I'm very delighted to be here at the AI Hardware and Edge AI Summit for the first time on behalf of Imagination. For those who don't know Imagination, we're a leading provider of embedded CPU and GPU IP, and we've been developing semiconductor IP specifically for the Edge for the last 20 plus years. What I'd like to talk to you about today is an approach that we feel is absolutely essential to deliver successful solutions at the Edge. This extends to AI at the Edge, and this is commonly thought of as system thinking, hardware, software, co-design. We like to think of this as a software-first mindset. Now, the irony is I'm not going to start with software. That's not lost on me. But please bear with me. It is going to become clear, even with my British accent. So why do we care? Well, if we look at the market data for the next 5 years, this is clearly in growth and in demand. And a lot of this is driven by increasing demand for autonomy and machine intelligence at the Edge. So as we look at this growth path, this is the market excluding personal computing, but a lot of growth is driven by advances in the automotive and industrial sectors. And this is where Edge autonomy really comes to bear. And for me, not only is it an important commercial opportunity, but it's an opportunity to do good for the societal impact this will bring, not just through productivity benefits, but through enabling experiences and the ability to do things that weren't previously possible. So as I say, this company's Imagination, we've been developing solutions for the Edge for over 20 years. And today, the challenges are ever thus. They were 10, 20 years ago. They're all too familiar. It's about getting maximal performance out of the compute, memory, device characteristics as best we can. So when we think about performance efficiency, typically, we may think of synthetic benchmarks or headline numbers. And those are commonly what we buy products on, right? Bigger number, the better. We think that's going to lead to the best outcome in the device. But actually, when we think about deploying a lot of these compute and AI work cases at the Edge, what's more important is whole solution efficiency. Because your Edge device is actually running an awful lot of different types of workloads at the same time, and we have to balance those in the context of the whole solution. So for a GPU, on your mobile device, it may be rendering the UI, it may be involved in gaming, it may be doing traditional compute, pre-processing for some image processing step, or it may indeed be running something like a generative AI workload or an LLM. So it's really important that we think about performance KPIs, not at those synthetic theoretical maxima, but the whole solution end to end. And this is why a software mindset is so important, because we need to enable that and understand that before developing a hardware solution that will best meet that need. If we look at the trends going forward, what we see is an awful lot of compute, an increasing demand for compute, like levels we haven't seen before. And what that leads to is increased heterogeneity within the edge devices we see today. So how are we going to get there? Well, there's an awful lot of work happening around CMOS scaling. We're going to increase the number of transistors available on the device. TSMC has a recent roadmap predicting through advances in technology and packaging, using 2.5D, 3D stacked devices, we're going to get to something like 1,000 times the number of transistors in the next 10 years than we have today. At the Edge, possibly a factor of 10 lower than that, but that's an awful lot of compute packed into a very small space. Now, the issue with that is that, great, that reaches the performance goals, but as we look at these increasing advances in technology, as we go from gate-all-around transistors to fork sheet FETs to complementary FETs in the outer years, the energy efficiency rises, but the density increases are enormous. And thus power is the new limit in our overall system. So we've moved from a compute roofline to a memory roofline and increasingly to a thermal roofline. And that's not a surprise to anybody involved in embedded devices today, because even on your mobile, you'll be throttling your main processor quite often. But all of that leads us to need to optimize for the end solution, not just for a specific workload or element of a workload on the device. So as I think through these challenges during this talk, there are two lenses that I wanted to bring to the discussion. The first is a quote from a well-known Canadian computer scientist called Rich Sutton, involved in the field of AI research for many decades, who observed that the power of general methods is what's led to the advances in AI technology in the HPC space over a long time, because these general methods scale as the amount of computing scales with it. And what that really speaks to is needing to produce systems that have general capabilities, that are not hyper-optimized or have assumptions baked into them. So, we look at the AI space today and see the deep stacks of attention mechanisms or NLP, and we look at classical algorithms for training and how we use stochastical gradient descent to get to end solutions. And these are what have scaled through all these advances in technology. So when we think about the future of edge devices, we need to think about scale. The second lens is about open and the power and momentum that sits behind open communities and open collaboration. Now, I'm sure all of you are aware of a viral internal memo within Google about their perceived threat of open source models versus what they were developing in-house. And the fact that these are being developed faster, they're more customizable, but that's a microcosm of what's happening generally with open collaboration. And in the edge space in particular, a lot of our solutions, they're fragmented today. There's a need to converge around standards and open movements that allow us to make the progress we need. And as we think about autonomy, when we're deploying these in devices, in self-driving cars or in factory automation, we need to know that they're going to operate safely and reliably, and a degree of transparency in the entire software stack is needed to get there, and I'll talk a little more about that shortly. So if we tackle the first lens first, the bitter lesson. On the left-hand side, we have what's pretty familiar to many of you, a generalized view of an edge device model. And what we have are some CPU, maybe some memory, but a wide menu of domain-specific accelerators. And so you have a DSA for graphics, you have a DSA for image processing, maybe you have a DSA for video processing, some DSPs. You have a lot of point solutions that accelerate different types of workloads. If we go back to thinking about the thermal management challenge and the scale that we need to operate with, you start to think from a solution point of view how you light up very dense areas of the design. That thermal challenge is going to become very great. And in addition, how do you program this if you need to interoperate between these different devices? On the right-hand side, we have a view perhaps borrowed from the cloud design philosophy, where you have still more than one accelerator. You can't go fully general. But what we're doing is having a more regular array of DSAs that are tiled and structured in a way that eases that thermal management problem. It's more tractable to build within 2D or 3D die technologies. It scales, and ideally, it's simpler to use. The challenge with this is that we've taken a hardware-first view. We're assuming that on the device on the left-hand side is going to be easier to program and manage. We need to test that well before we implement the hardware design. So this is where, and in the words of imagination, we take a software-first view. We need to enable holistic workloads running on that device as early as possible. And when a developer takes a look at a platform, they need to understand that they can take the model or the workload or the algorithm they've been developing and run it on the end device. They don't want to spend a long time picking their way through software stacks, compilers, mappers, trying to understand how this works. It just needs to run. There's a need to get to market quickly. So what we need is some form of non-proprietary entry point using a common open stack and get something running. Then I want to check that it's actually working. Is my model output correct? With some of the quantization steps I might have applied, do I still get what I expected? How does it integrate with the other parts of the edge device? I still want to avoid optimization at that point because I'm just trying to get to a functionally correct output. So in order to do this, I need an easy-to-use interface. I need some idea of how I accelerate things on the device. I need some, in addition to libraries, some profiling, some tooling that will help me with that. And we start to transition to the third phase around optimizing performance. But at this stage, what we need is sufficient degrees of freedom within the software stack, within the device, to go from functional to performant and then optimal. And so as we think about how we approach that as a developer, I need the relevant information from my hardware, so I need to expose counters and profiling and debug information. And I need the right flexibility at various points within the software stack to be able to optimize for that. And so this is where, in the context of AI, we might look at kernel batching techniques. We might think of how we segment memories in the device that give you flexible access to the memory that's available. There's various techniques we might use, but we've got a full flow from supported through to optimal. So how might this look if we were to build on some sort of open collaboration? Well, there is one. It's called the Unified Acceleration Foundation. It's derived from Intel's One API effort that was donated to the Linux Foundation and provides a path for multi-architecture, multi-vendor ecosystem for various hardware accelerators. Imagination is a founding member. It's been a strong proponent of this foundation for some time, and it allows for common open development to the common parts of the stack, whilst giving some focus on the differentiation that's very close to the individual accelerators and edge devices that are built on each contributor's technology. So how does this look in practice? Well, this is, again, a very high-level view of how this might look. So typically, today, developers are training and building models on NVIDIA hardware. So they're either looking at general machine learning frameworks like PyTorch or TensorFlow, or they have some CUDA reference code that's running on an NVIDIA device. I need to get that running on my non-NVIDIA edge device. How do I do that? Well, within the UXL framework, there's a tool called Cyclomatic, which will take CUDA code and convert it to an open standard called Cycle, which is a hardware agnostic library under the Chronos standards group. And that allows me to target immediately to a CPU. So it's going to run, it's flexible, it's not performant, but it's a baseline from which I can get something running. So we tick the box, it's supported. Then I want to think about how I get it running on my own piece of hardware. I can use this framework, but as Imagination or as a provider of hardware, I can focus my efforts on the really important, highly optimized, highly differentiated part of those libraries that when I convert to Cycle, it's going to run really, really well. So I need to provide some equivalent CUDA libraries like MKL, so math kernel libraries, fast Fourier transforms, basic linear algebra. So there's a collection of libraries that make sure that the translation from Cycle to this, from CUDA to Cycle will run pretty well on a different device. There's then the possibility of graph compile methods being lowered onto the same hardware device through the 1DNN framework. So it's possible through an open ecosystem to take what's very commonly developed against hardware in the cloud and then run that on the device very quickly. And you can provide extensions that will give you finer control of the hardware within this API so that you can get to that optimal solution very quickly. So that all sounds great, but there's an awful lot of things that need to come from the provider in order to make this a reality. So we've talked about being able to leverage the open source, and that gives you the speed of development. It gives you pace and the flexibility to be able to intersect with, community-generated frameworks. But now what I really want to do is do that earlier. So I don't want to wait till I have the edge device. I want some idea of how it's going to run way before I bake that in my hardware. I want to shift left. I want to be de-risking a lot of the development effort by doing this on model. And when I talk about models here, I mean approximations of the hardware, not AI models. So the more insight we can get from modeling, the more we can derive insights earlier in the development cycle and speed up the time to overall optimal output. There's also the case of trying to lower things through different levels of the software stack. I may want to take an integration much higher up, so at the at an adaptation level perhaps between an ML framework like PyTorch, but above the compiler or mapper. Or I may want to integrate very low down in the stack, because if I'm safety conscious and I have a safety critical application, I really need to know what my code is doing all the way down to the metal. I want to intersect much lower. So these toolkits that are created make very clear the entry points to different levels of the stack and provide flexibility to customers to be able to integrate accordingly. And all of this is providing the possibility and the insight to derive flexible architectures going forward. So when we talk about dynamism in an edge device, we're thinking about how do I run several different workloads at the same time? How do I run direct programming models at the same time as graph compiled models? How do I think about dynamic tensor shapes and sizes? All of this flexibility is needed in the edge device, and we can start to bake in the hardware, because we've taken this software first view, all of the mechanisms we need. So I spoke at the beginning about the advances in industrial and automotive segments. And what's really driving that is, as I said before, this edge autonomy that's making factory automation possible, self-driving cars, automated delivery vehicles. This adds new dimensions to the edge problem, because now, instead of this traditional human-to-device interaction, we have device-to-device interaction, and we have device-to-environment interaction. So these common KPIs like tokens per second, time to first token, these inner KPIs, they grow massively now, because we're not doing this at rates that humans and machines interact. It's machine to environment. So what does that mean? It means the demand for computing is even greater at the edge. So all of these initial problems of trying to manage thermal limits are even greater. And so we need to think about this ahead of time. The second issue is safety. So if you're running something on your phone and there's a pixel error or a compute error on your phone, it's not really going to matter whether that's right or wrong. If we start deploying something like this in an AI algorithm in a car, hallucinations that come from these models, errors, faults, we need to know about them very quickly, and we need to correct for them. So there's a whole layer of interpretability and resilience that we need to build into our edge solution when we start deploying solutions for industrial and automotive applications. So what does this mean? Well, if we take a software-first mindset, we think about how we address functional safety and faults and creating resilient hardware. When we do that, we realize pretty quickly we don't really want software to have to manage checking and understanding that there are errors occurring in the end solution. So we actually want to bake in some hardware mechanisms that do that for us. So when we think about functional safety innovation, we're going to perhaps apply error correction codes on memories. We're going to add parity bits to buses, but we're going to create some mechanisms that allow us to check for errors in the design, agnostic of hardware if we can. Then we need safety within the AI models themselves. Now, there are whole fields of research covering constitutional AI, explainable AI, all around how we create models that are resistant to tests of inputs for general methods, generalized methods, how we can ensure that these models don't produce invalid outputs and don't conflict with safety objectives that are baked within the overall device's assumptions of use. All of this needs to be thought of ahead of baking in any mechanisms or features within the device. And then, of course, we're doing all of this in the context in which this edge device operates. So, be it in the specific factory or the specific shop or with the specific user, the context is very, very important. And we can't tune a model, in the cloud with all of this real-time data that's coming in from the system. We need to be able to do some of that very close on device, where latency is critical, privacy is critical. So techniques like retrieval augmented generation and balancing what gets done on the device versus what gets done in the cloud is critical. And all of this requires open modifiable software, because as we think about safety critical deployments, we need to know right down to the metal what the hardware is being instructed to do and how it's going to behave. So, why is that exciting for imagination? Well, as a company, we've been developing edge IP for over 20 years. We've been developing IP for safety critical systems for more than a decade. We have a lot of our IP running in cars today and have thought with this software first mindset how to develop solutions and IP specifically for the industrial and automotive sector in particular. So just to recap, there's a huge opportunity at the edge. Reasons like this conference exist today because of that huge opportunity, and that opportunity for good is enormous. Hardware will continue to innovate. There'll be advances in processing technology, advances in package design, advances in how we bring hardware devices together. But in order to make this realizable at the scale and at the pace and with the transparency needed at the edge, we need to drive open collaboration and defragment what is a very wide ecosystem and converge around open standards, like UXL. Autonomy only exacerbates the situation in terms of the compute and memory and thermal challenges that exist today, which makes this solution software first thinking even more important. And therefore, imagination is a very, very credible partner to deliver IP that makes you and other customers successful at the edge. If you'd like to know more, I'll be at the booth 20 in the expo after this. Thank you very much for listening to me, and I hope to speak to you again soon.